We know the blast furnace breathes through its hearth, but it's the cast house that determines its pulse. We often focus on the top gas chemistry, but if we lose control of the crucible, the rest is academic. So today we are not just talking about tapping iron, we are integrating internal fluid dynamics with the taphole engineering. So by end of this session, you will gain three critical deliverables. First, a quantitative understanding of the ticking clock that govern tuyere flooding. Second, a mechanical breakdown of the ejector choke phenomena that paralyze the burden descent. And third, the precise material anatomy of taphole clay required for laminar extraction. On the title slide, so look at the glowing hearth cross section. The orange core is not just heat, it's a high pressure fluid system fighting for a path out. We are here to master that path. So, to master the flow, we must first map the physical reality inside the crucible. Now look at the cross section on the left. We have a multi-phase system where liquid iron and slag separate naturally within a coke-filled hearth. Now notice the density delta. Hot metal is at 7.2 tons per cubic meter settled horizontally, while the highly viscous slag at 2.3 ton per cubic meter float on the top, forming a sharp downward slope towards a active taphole. Factor here is the residual volume. At the end of a typical 60 to 240 minute cast, a massive amount of slag remains trapped because of this slope. This is not just leftover material, it dictates the intermediate urgency of your next cast. If you miscalculate the slag slope, you miscalculate your available hearth capacity, leading to a dangerous reduction in internal voidage before the next hole is even drilled. This residual volume is the primary driver of your uh, most critical metric, the time remaining until catastrophic failure. So every minute the taphole is closed, the clock is ticking. So this slide represents our reference furnace parameters for 12,000 ton per day operation. So look at the escalation bar on the left. It start at 0 minute with a dry hearth and hit at 79 minutes for catastrophic tuyere flooding. Our total volume from the taphole to tuyere is 812 cubic meter, but because the hearth is filled with a coke only, 20% of that, or 162 cubic meter, is actual fluid capacity. With a liquid production rate of 124 cubic meter per hour, your margin of error is a razor thin. The operational impact is tremendous. So if your gap time exceeds 79 minutes, fresh liquid flood the tuyere, causing immediate equipment failure and multi-day outages. We manage the gap time to preserve the tuyere, but a flooded hearth does more than just melt copper. It shifts the furnace physical mechanics. When liquid rise too high, they trigger a mechanical disaster known as a ejector choke. So what is that ejector choke mechanism? So follow the transition from a panel A to panel B. In normal operation, gas and coke flow freely toward the tuyere, but look at the panel B. As slag level rise, this submerged coke exert a massive upward buoyancy force. So this buoyancy compresses the cohesive zone, reducing coke voidage and essentially paralyzing burden descent. So this is the ejector choke. So what it result is massive. It has a cascading failure. Wash gas can no longer move through the center, so it deflects to the wall, driving extreme heat losses and causing blast pressure to spike uncontrollably. So you are not just losing production, you are stabilizing the entire structural integrity of the blast furnace. This mechanical paralysis is why dry hearth casting is not a suggestion, it's a thermodynamic necessity to maintain a stable blast furnace and consistent burden descent. So maintaining that dry hearth require a taphole that can withstand these extreme pressures without failing its integrity. So these structural bottlenecks is taken care by the taphole clay. So the taphole is more than a hole. It's a precision engineered valve, we can say. So observe the mushroom skull highlighted in orange. This proactive layer of solidified iron and clay is what keeps your refractory from melting. So look at the six condition for the safe extraction on the right. We need a consistent 812-degree angle to access the deepest part of the hearth without causing excessive runner splashing. So this is the number one and most wanted point. So if we have gas leakages between the shell and the refractory, it accelerate internal wear and risk a breakout, and the consequences leads to a factor here is on about the taphole life. So every time you have a false blow or a secondary crack, you are losing the structural integrity of the mushroom. So without a stable mushroom, you cannot achieve the complete liquid evacuation required to reset that 79-minute ticking clock we just discussed. The durability of that mushroom and the stability of the extraction depend entirely on the chemistry of the clay you push into it. So look at the material anatomy matrix. So we are not just using a mud, we are using a composite of SiO2, carbon, alumina, silicon nitride. So notice the operational impact of the carbon bonding. Tar bonded clay cures slowly, but resin bonded clay cure 10 to 20 times faster. For single taphole operation, resin is non-negotiable. There is no doubt about it. And as far the silicon carbide is concerned, silicon carbide is our expensive sealer. It reacts with the FeO in the slag to actively expand and lower internal porosity. The so what is simple. The wrong clay chemistry leads to higher wear rates, which means your taphole diameter increases during the cast, and this turns a controlled extraction into chaotic torrent, making it impossible to transition from turbulent to laminar flow in the troughs, ultimately risking a granulator explosion downstream. So even the best clay chemistry is useless if the mechanical delivery doesn't create a perfect seal. So slide 7 illustrates the high stack moment of closing the hole. The clay gun must perfectly counter the immense internal furnace gas pressure. We use a compressible wooden laminated ring to seal the uh, uh, taphole and taphole face gap between that is in between gun and taphole face. So post press phase, let us discuss. After the main volume of the clay is pushed by the ram, we hit a microsecond post press spike. This drives clay deep into the secondary micro crack to heal the mushroom. So if this seal breaks, as shown in the spillage thread box, internal compression is lost. The result is a failed plug that will require destructive oxygen lancing to open. We use this mechanical force to mold the internal valve, ensuring that when we drill the next time, the clay has cured into a rigid, predictable cylinder. Once that cylinder is cured, we have to drill through it with the surgical precision. On the left, you see standard drilling. Notice the red vibration wave. A 4-meter drill rod bend and oscillate, creating a extracted diameter much larger than the bit itself. This leads to erratic, high velocity cast. Self-guided drilling uses a stiff sledge mechanism to track perfectly straight. Look at the critical thermal control note at the bottom. We use nitrogen cooling mixed with a precise water mesh to save bit from oxygen exposure. However, the water must shut off instantly when the nitrogen stops. So, what is the factor? So, if moisture enter the taphole, it react with the hot metal, causing a steam-driven blowout that can destroy the taphole face and injure the crew. We are drilling for a calculated diameter to ensure a predictable cast duration. The quality of that drill path and the clay's wear resistance determine the shape of your cast curve. So coming to our next slide, so let's look at the data. On the left, a good clay has a wear rate of 0.15 mm per minute. The hot metal volume is stable and the slag begins early. Most importantly, the maximum hearth level peak at a safe 1.0 meter. Now look at the poor clay with a 0.30 mm per minute wear. The initial flow are suppressed and slag flow disappear mid-cast because the hole is wearing too fast and losing suction. This causes hearth level to spike dangerously to 1.5 meter or more. When that level spike, you are back in the ejector choke zone. So poor clay is not just a maintenance issue, it's a liquid maintenance and management failure that forces the furnace to retain massive residual slag volume, shortening your next window of operation. So if the clay holds and the flow is controlled, the final challenge is separating that liquid in the trough. So coming to the physics of separation. So once the iron leaves the furnace, we must manage the transition from turbulent to laminar flow. Near the taphole, the flow is turbulent and chaotic. By the time it reaches the skimmer, it must be laminar. To ensure perfect separation, prevent catastrophic granulator explosion, the hot metal slag interface line must remain strictly 10 cm above the skimmer opening and 10 cm below the slag dam. So these factors contribute towards your extraction rate. When it's too high, meaning your taphole is too large, the flow remains turbulent and slag will carry over into iron runner. This not only ruins your hot metal quality but also causes a massive refractory damage in the runner that were never designed for slag chemistry. So maintaining this 10 centimeter balance requires us to master the gap time between casts. So to chart show, if you'll see this chart shows three distinct scenarios for the hearth management. Scenario one is our baseline, which is 4-minute gap time and a 60 millimeter beat. This keeps the hearth level at a perfect 1 minute. As far as scenario 2 is concerned, here a 30-minute delay causes a complete loss of control. So slag is permanently trapped above the tuyere level. So to recover, we use the intervention, we increase the drill bit by 10 millimeter. So this restricted the hearth level to 2 meter. But look at the note at the bottom. Increasing the bit is an emergency intervention, not a fix. It takes 5 consecutive casts to come back to a normal diameter. So the operational impact is a massive surge in runner wear and a loss of slag separation efficiency. We use the bit size as a lever, but it's a lever that lever with that price tag. Uh, so to know when to pull that lever, the control room needs a clear vision of cost tracking. Now coming to the our cost tracking chart. So this is your dashboard of hearth health. Uh, as you can see, look at the pattern A, the ideal baseline. Notice the consistent overlap between taphole and thick taffoles and thick continuous slag band. So this means we are draining the hearth faster than we are feeling it. Now look at the pattern. See the danger zone. These shortened orange block indicate that slag is not draining. This point directly to poor internal voidage or an incorrect taphole length. So here is a predictive outcome. If you see the pattern C developing during the morning shift, you know you are heading for a back-to-back bottleneck by the afternoon. This chart allows us to shift from reactive firefighting to proactive cast house drainage management. So when the chart moves into danger zone, we trigger our rapid responses protocol. So coming to our next talking about these uh, rapid responses protocols. This is our decision tree for a crisis. If node 1 shows no slack drainage, path A is to enlarge the next drill bit. If that doesn't work, node 2 asks, is it a dry cast? If not, we execute an overlap cast by opening a second taphole. So if the hearth is still not draining, we must drop the wind rate to prevent tuyere flooding. Notice the production drop. You are capped at 8,000 tons per day if you are focused into a single taphole shift. So every hour you spend in this protocol is costing the plant thousands of tons of iron. We use this step to protect the asset, but the goal is to never reach node 3. If all these protocols fail, we are left with the most dangerous tool in the cast house, the last resort. That what is being shown. So let me clear. Oxygen lancing is a catastrophic invention, not a standard procedure. We all know the graphic shows a lance straying. It is a physically impossible to burn a perfectly straight line manually. So the lance melt the taphole block and, as shown in the consequences box, destroy the surrounding copper cooling steps. So this factor is a multi-day taphole damages activity, and which takes a lot of time. So repeated lancing carves secondary cavities inside the mushroom, which leads to massive molten breakout. So if you find yourself reaching for the lance, your process has already failed. We use the science of clay and drilling to ensure that lance stay on the rake. So to avoid the lance, we must close the loop on all the physics we have discussed. So coming to, we conclude with the continuous extraction loop. It starts with a voidage balance, a 79-minute buffer that dictates the rhythm of the entire plant. Second, we maintain the taphole integrity through the precision drilling and high performance clay. Third, we ensure laminar extraction by managing trough geometry and the 10 centimeter rule. So finally, we exercise gap time control to prevent the ejector choke effect. The ultimate takeaway is this: the cast house management is not merely reacting to metal flow, it's a proactive manipulation of multivariable physics to keep the blast furnace breathing. So master the cast and you master the furnace.